Now, in upper level mathematics and physics, we work with something called orbital mechanics. Obviously, it has the word orbit in it. It's very useful for things like astrophysics, but it's also useful for things like electromagnetic theory, some mathematics applications, etc. And that's a different approach to conic sections. It uses something called the eccentricity directrix approach. Oops, sorry. And by switching to this approach for writing conic sections rather than the Cartesian approach, which is what we've done up to this point with the x's and the y's and things, it allows us to have a more unified way to write all of this. I'll just get rid of the word more and just say unified. It allows us to have a unified way to write all of this. And that will make things easier for us in those later applications courses where lots of physics and orbital mechanics are involved. All right, so how does this work? Well, we have F, which is a fixed point called the focus, sounds familiar, and let L be a fixed line called the directrix in a plane. And then let E be the positive number called the eccentricity, and then the set of all points P in the plane such that PF over PL, where PF is the distance from the point to the focus, and PL is the perpendicular distance from the point to the directrix L. If we take the ratio of those values, we get E, which is the eccentricity. Now, if your eccentricity is equal to 1, that makes a parabola, right? If it's always the same distance from the focus to a point and the point to, and that's a perpendicular distance, so that forms a perpendicular right there. So if that happens where it's always equal, that's the definition of a parabola, right? That they're always equal to 1, right? They're always equal, so therefore the eccentricity is equal to 1. Now, if it so happens, right? So here, let me just kind of highlight these. So if the green, which is FP, and the orange, which is PL, so PFPL is always the same, right? Then that's, right, if this and this are equal, great. But what if PL is a bit longer, right, than PF? What if this is 1 and, just for the sake of it, this is 2, right? What if that's longer? Well, then when you take PF and you divide it by L and you get your eccentricity will be between 0 and 1. So, right, because the orange is bigger than the green. Okay. So that would get you an ellipse, right? So here's your green, here's your orange. All right. Now, what about on a hyperbola? Well, it's a little bit trickier. So the focus to the point, and it could go either direction, really. So if I take FP, that distance right there, that's green, that's longer, so I'm going to give it a double mark. And this distance right here is shorter, right? And it would work even if you went to the other side, right? This distance right here from point to L is shorter than this distance, which is longer, right? So you're going to get, when you take PF divided by PL and get the eccentricity, that eccentricity would be greater than 1. And that would get you a hyperbola. Now, in particular, eccentricity is very useful for ellipses. When we look at an ellipse, and this is particularly true for astrophysics, when we look at an ellipse and we play with the size of the eccentricity, we're playing with the ovalness of the ellipse. And I actually have an applet that we might look at later as well for Kepler's laws for planetary motion. I'll put the link to this in Canvas for you. But over here you can see this is a planetary orbital simulator. So here's a planet going around a star. The planet's right there. Right, there's your planet going around. And then the eccentricity is the path that it's following. It's following an ellipse, but I can play with the eccentricity. So if I make my eccentricity go lower, it becomes almost a circle. But if I make it go higher, it changes it and makes it more oval, right? So that path is much more oval than the original path because the eccentricity is a higher value. Now notice the eccentricity is still a decimal lower than 1. It has to be because it's an ellipse, right? And we just saw on the previous page that, right, the eccentricity for an ellipse has to be between 0 and 1. Just to make it clear, we could highlight a couple of these just so you can see the difference. So this one, this kind of purple that I'm putting in here, this big one, that would be an eccentricity of 0.8. Whereas this one right here would be an eccentricity of 0.6. Right? They have the same focus and they have the same directrix, but the eccentricity really affects the ovalness of the ellipse. So let's look at some properties of ellipses and hyperbolas that are centered at the origin. So for various reasons, when you're working with orbital mechanics, a lot of the time, especially for our purposes, we would center it at the origin because it just makes everything easier, right? So why not put the origin wherever you want, because it's a made-up grid system anyway. So we can see we have all sorts of formulas for the foci, right, on the x-axis, the y-axis, right, whether they're major or minor, etc. And then, right, these are the vertices, and then these are the foci, right? And the directrixes, and so on. So you have the length of your major axis, which is 2a, the length of your minor axis is 2b, 2c is the distance between the foci. So it's very similar because it's built on the same pieces that we were working on before when we were working strictly in the rectangular system, and we weren't working with the eccentricity and directrix. So for ellipses, b squared is equal to a squared minus c squared. So b squared would be equal to ultimately a squared times 1 minus e squared. We already saw this piece earlier, this first line. We saw that before. And then for hyperbolas, b squared is equal to a squared times e squared minus 1. And if e is greater than 0 is the eccentricity, then e is equal to c over a, which is a over d. Keep in mind that all of this only works if the center is at the origin, in particular this piece down here. So if the center is not at the origin, we have other problems. And then most importantly, what we just saw, if the eccentricity is less than 1, it's an ellipse, equal to 1, it's a parabola, greater than 1, it's a hyperbola. So let's look back at the orbit with the perigee and apogee of the Earth and the Moon. Now before we do anything, let's think about this for a second. We know that the ellipse has, it's very close to circular. The Earth is quite close to the center. So let's just make a note of that. So we know what we should expect here if we are looking for the eccentricity, right? So the ellipse is very close to circular. That's why for thousands of years astronomers had such a hard time figuring out our orbits. Very close to circular. It's not circular, but it's very close. So a low eccentricity is expected, right? In other words, close to 0. Right? If you think back to this piece we just saw, we expect the eccentricity to be on the low side, right? Looking very much like a circle. Not quite a circle. That star is not quite in the center, but it's getting there. Okay. All right, now let's remind ourselves, this is from a previous example, that A was 384,400 kilometers, and B was 383,820 kilometers. And just flipping back to that example real quick, right? So there was A, there's B. C we found to be 21,108. Okay, so what is our eccentricity? The eccentricity is equal to C divided by A. C divided by A, which would be 21,108 divided by 384,400. So let me grab Desmos. And there we can see we have an eccentricity of 0.0549. And just out of curiosity, let's make that happen. 0.055 is roughly, there you go, that's roughly our orbit. So you can see how that looks. right? But in this case, of course, the Earth would be that dot, not the, that's not a star, that'd be the Earth, and that would be the moon going around us. And again, E is a very small number because the moon's orbit is so close to circular. It's not exactly circular, which means, of course, sometimes the Earth is closer to the moon than others, which is why we have differences in tides, right? Some tides are bigger than other tides, and that's partially why, because the moon's gravity is pulling on the oceans. Let's look at an application of eccentricity with conics. Namely, we can use the eccentricity to find the circumference of an ellipse. The circumference of an ellipse has this formula. I'm not going to derive it. You're just going to have to believe me. That it's equal to 4a times the integral from 0 to pi over 2. There we go. 4a times the integral from 0 to pi over 2 of the square root of 1 minus e squared times sine squared theta d theta. Okay, where e is the eccentricity, which is c divided by a. And you can kind of see the logic of it. What you're doing is you're finding kind of the circumference of a quarter of the ellipse and then multiplying it by 4. All right, so we're going to set up the integral, and we're not even going to attempt to do it by hand because it mentions to use technology. That must mean it's pretty atrocious, so we're not going to bother. Okay, so let's set this up. So we know that we have x squared over 25 plus y squared over 16 equals 1. So we know that a squared is 25, so a is 5. B squared is 16, so B is 4. Now, to find C, we know that B squared equals A squared minus C squared. And so therefore 16 equals 25 take away C squared. So C squared is 25 take away 16, which is 9. And so C is equal to 3. Now putting all three of those pieces together, I know that my eccentricity is C divided by A, which I can now see as 3 divided by 5. Okay, so we found all of those components. So now let's look at our circumference formula. So circumference is equal to 4a integral from 0 to pi over 2, the square root of 1 minus e squared sine squared theta d theta. Okay, so that's 4 times 5 integral from 0 to pi over 2, the square root of 1 minus 3/5 squared would be 9 over 25 sine squared theta d theta. Actually, I think what I'm going to do is write this as 3/5 and put a squared next to it, just so we're not skipping any steps. Okay, so the whole thing becomes 20 integral from 0 to pi over 2 of the square root of 1 minus 9 sine squared theta over 25 d theta. And then we're just going to go stick that into technology as requested and make it find it for us. As I'm typing this in, I'm just going to remind you that you hit the squared after the sign, and then you want your angle. So you can just say theta, T-H-E-T-A, and it will build it. And then you want that piece divided by 25. And then at the end, outside of the square root, you want to make sure you type d theta. There we have it. And we get about 34.07. Oops, that's a plus in there. I meant to write a minus in there. Sorry about that. There we go. 28.36. There we go. All right, so, and now the units would, of course, be kilometers. because circumference is a length, right? It's the distance around the orbit, but it's only in one dimension, length. It just curves around the circuit.